Swayam Prabha. Digital India. Educated India.
Welcome. So in the last class we have started studying linear program, and we are doing some basic background of preliminary of linear program. So we will continue that in this class also. So there is something called standard form of a linear program. It turns out that every linear program can be written as this standard form. What is this form? It is minimize b1 x1 plus dot 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 bn xn subject to linear constraints a11 x1 plus dot a1n xn is greater than equal to, let us call this b1 and let us change this name c1 to cn, a21 x1 plus dot a 2n xn is greater than equal to b2, so on, am1 x1 plus dot 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 mn xn greater than equal to bn, and these variables x1 to xn is greater than equal to 0. Okay. So this is a standard form, and it turns out that every linear program, it could be a maximization program or any other program, can be converted into this sort of form with equivalent or transformation. So for example, we can define x1 equal to minus x2 and the minus y1 and so on. So with this sort of linear transformation, we can convert or write down any linear program into this standard linear program, and that's why this linear programming theory has been developed with respect to this standard form. So with respect to this standard form, what is the dual linear program? So again, let us follow the same approach. We multiply first equation with y1, second equation with y2, and third equation with ym. So we maximize b1 y1 plus b2 y2 bm ym subject to what are the conditions? That when I multiply this, the coefficients of x1 multiply and sum this m equation, the coefficient of x1 should be less than equal to the coefficient of x1 here. So the condition is a11 y1 plus A 21 y1 y2, A m1 y m, this is less than equal to C1. Similarly, A 12 y1 plus A 22 y2 plus A m2 ym is less than equal to C2, so on. The last one is A1 n y1 A2n y2 Amn ym is less than equal to Cn, and of course y1 to ym, this is greater than equal to 0. Okay, now we state an important result which is called complementary slackness. Complementary slackness condition. It gives us a certain criteria when a solution, a feasible solution, is an optimal solution. So, okay, by the way, so this matrix, this is called, so if this matrix, if I write A equal to A 1 1 2 A 1n, A m1 2 A mn, this is called the coefficient matrix. Okay, so let x, that means x1 to xn, and y equal to y1 to ym be primal and dual feasible solutions respectively. Okay, then both x and y are optimal solutions if and only if the following conditions are satisfied. So, what are the conditions? We have two set of conditions. One is primal complementary slackness conditions, so what are primal complementary slackness conditions? It's like it says for each variable j from 1 to n, primal has the variables x1 to xn, either xj is 0 or, now notice that for each variable xj there is a constraint in the dual, and the primal complementary slackness condition says that either the variable is 0 or if the variable is not 0, then the corresponding constraint inequality must hold with equality, or summation, if xj is not equal to 0, the jth constraint corresponding to cj, this constraint should hold with equality, or summation a j aij aijyi I equal to 1 to m, this will be cj. So, this is the primal complementary slackness conditions. These conditions should be satisfied, and the dual complementary slackness condition. This is because the dual of dual program is primal. What do you mean by that? You convert this dual program into standard form and then write a dual of it, and it will be same as the primal program. So, here also for each the variables are y1 to ym, for each I from 1 to m, either yi equal to 0 or the ith constraint, which is aij xj j equal to 1 to n, this must be equal to bi. Okay. So, this is the complementary slackness condition. This will be we will crucially use in our design of approximation algorithms. Okay. Now, what is the high level idea of how to use linear programs in designing approximation algorithms? So, there are two broad approaches. Approach 1, often the optimization problem at hand can be written as an equivalent integer linear program. Now, what do you mean by that? Integer linear program is a linear program which has a linear, again like linear program, it has a set of variables and we have optimization function which is a linear function over the variables, and we have a linear set of constraints, but the variables, some of the variables can take only linear or only integer values. So, let us understand this with an example. So, for that let's recall the vertex cover problem. For example, consider the vertex cover problem. Recall, in the vertex cover problem, we are given an graph G and we are looking for a vertex cover of minimum size. So, for that, so the following integer linear program captures the vertex cover problem. The set of variables are, the set of variable is xv, where v in set of vertices. So, for each vertex in the graph G, we have a variable, and the idea is that variable takes only 0, 1 values, either 0 or 1, and if we pick it in the vertex cover, then we set the variable to be 1. So, to find the minimum size vertex cover, we minimize summation xv, v in vg, and what are the constraints? Subject to for each edge one of its vertices, one of its endpoints must be picked. So, that means xu plus xv, this is greater than equal to 1. Okay, for each edge. So, if I have m edges, I have m number of constraints, and the variables take value in 0, 1. In linear program, variables take value in a real interval, but in integer linear program, variables can take value only in integers. So, this is for all v in vg. So, this is a ILP formulation of the vertex cover problem. So, it turns out that many optimization problems can be written as an integer linear program. Now, what we do, but integer linear program, solving it is NP hard. Finding an optimal value is NP hard. We do not hope to have a polynomial time algorithm for integer linear programming unless P equal to NP, right? However, integer linear programs is NP complete. Okay. So what we do is that we relax the integrality constraint. So this is the ILP, integer linear program. Now we relaxed it to an LP. Relaxed LP. What is the relaxation? Everything is same except the variables. Instead of allowing them to take value only 0 and 1, we allow them to take any real value in between 0 and 1. Minimize summation xv v in Vg subject to for each age e equal to u comma v xu plus xv is greater than equal to 1, and for each vertex v in Vg xv is in between 0 and 1. Now clearly, because the search space is more, the search space is a superset for integer linear program compared to the integer linear program, we clearly have LP opt is less than equal to ILP opt, but ILP opt is nothing but opt, because ILP is a equivalent formulation of the given optimization problem. So using this framework, we get the lower bound that we are looking for. Hence, this framework gives a lower bound on opt, which is often the first step in any design of approximation algorithm. Okay. So next what I have then we solve LP. So the idea is solve LP in polynomial time that can often be done because linear programming is in P. Every linear program can be solved in polynomial time. That means an optimal solution can be found in polynomial time. Okay, and then but this solution will have a fractional solution. So however, the solution will be fractional in general. So then what we do is that we apply in some sense what is called rounding technique. From this fractional solution, we create a solution of the optimization problem. We create a solution of ILP, which will automatically give us a solution of the optimization problem, but which may not be the optimal solution. So the final step is we round the fractional solution to obtain an integral solution, which in turn provides solution to the given optimization problem instance. Provides approximate solution given optimization problem instance. So here in this approach, the ratio between LP opt and ILP opt, this is the lower bound on, this is a bound on maximum approximation ratio possible. So this is called integrality gap. Integrality gap is supremum over all instances, ILP opt or opt of I by LP opt, because we are using our LP opt as the lower bound. So this alpha, this approach can provide an approximation factor of at most alpha, approximation factor of at least alpha for minimization problems. This is for minimization problems. Okay, and the second approach is use this primal dual approach for designing or analyzing combinatorial algorithm. So approach 2 use LP and its dual LP to either analyze a combinatorial algorithm. An algorithm is, loosely speaking, it's called combinatorial if it does not solve a linear program. To either analyze a combinatorial algorithm or design a combinatorial algorithm. So in this approach, we do not directly solve linear program. So in the next couple of lectures, we will see design of approximation algorithms using both the two approaches. Okay, thank you.